Okay, good morning, everybody. So today we're going to be starting into Chapter 5, Section 1. And personally, this is my favorite thing to talk about that I discuss in the entire school year with you. I feel that this is the most important thing that you could hear from me, especially because many of you are seniors and you're getting ready to graduate high school and make a pretty big financial decision that's going to affect your life for quite a few years after high school, much past where my age is, which right now I'm 40 years old. So this and what we're going to talk about is extremely important. So we need to do a little bit of build up to the actual activity that we're going to do. And that build up involves me teaching you a little bit about exponential functions and how they grow and what their graphs look like. And then that'll transition into us discussing taking money out for loans, investing, and things like that. So the first thing we want to talk about is what an exponential function is. And it says, so far, this text has dealt mainly with algebraic functions, which include polynomial functions and rational functions. But in this chapter, you will study two types of non-algebraic functions, exponential functions and logarithmic functions. And these functions are examples of transcendental functions. And they have some different attributes than the other algebraic functions that we've studied so far. So what they show you in this box is the basic form of an exponential function. And so you have this f of x equals a to the x. Now, a right here is not normally going to be a variable. Normally, a will be a number. And for an exponential, for this particular exponential function, the way they're describing this, a has to be greater than 0 and a cannot be 1. There's a reason for that, and you'll kind of see a little bit later. But the short of it is, if a was 1, it didn't matter. It wouldn't matter what you took that 1 to. Any power, it's not going to grow or shrink. So we either need a number that's from 0 to 1, so it could be 1/2 or 3/4 or 7/8 or 1/8 or anything like that, or anything larger than 1, 2, 3, 4, 5, like that. Okay. Now, the next thing we're going to take a look at is how rather, to type these into your calculator. Now, it might seem like a basic thing, but we need to make sure that you are familiar with this because we will be filling out various tables and stuff to do this. So I'm going to pull up my graphic calculator here. You can see that. And they want us to evaluate. It says use a calculator to evaluate the function at the indicated values of x. So the first one, we have this function f of x equals 2 to the x power, and they want x to be negative 3.1. So I'm going to simply type 2 and then to the, now my particular calculator puts a little box there so you can see I'm going to fill that in with negative 3.1. And it's that easy. If you have the TI-83s where it puts the caret, make sure you put parentheses around whatever you're taking to a power. And I'll show you that in a second why that is in one of these other examples. But make sure you put parentheses around what you're putting in for a power if you have the TI-83s, which just show the caret as the exponent. When you hit enter, you can see that's 0.1166. So this is equal to, whoops, that's the wrong thing here. So f of x would be 0.1166. Okay, the next one, you can see we have f of x equals 2 to the negative x. So we're going to plug in pi for that one. So once again, we're going to hit 2, then hit the caret. We need to press negative and then the pi symbol, which is right above the caret. So you do want to put the pi instead of the 3.14. It'll be more accurate. And this one, f of x, is equal to 0.1133. Now, the last one, and this is why I was saying about for the people that have TI-83s, you should make sure that you're putting parentheses around what you're putting in for the exponent. If you were to, in a TI-83, just do 0.6 and then press the caret, and then you did 3 divided by 2, what your calculator is going to do is it's going to do 0.6 to the caret, and then it's going to take that to the third power, and then it will divide that answer by 2. So it will do this first, the TI-83s will. unless you get your parentheses around that power. And this is why I was saying for the TID3 people, it is important that you put parentheses around the entire power. Now you're forcing it to do the PEMDAS order that you want, which is to take the 0.6 to the power. So when you hit enter there, you get f of x is equal to 0.46475. So we're going to go ahead and say 465. And there's your answer for that. This is pretty simple. You guys should know how to do that. All right, so now let's take a look at what a graph of an exponential looks like. And the way we're going to graph this exponential is I'm actually going to make a little table for you so you can see how this works and what the difference is. Now, with an exponential function, we start with, we're going to start with a table that has an x equals 0. So I'm going to go ahead and make a table for this, xy, is we're going to start with -2, -1, 0, 1, and 2. And then I'm going to make another table, circle the first one in red, make the second one in blue so we know which one goes with which. And so we'll have an xy, we'll do the same table, -2, -1, 0, 1, and 2. Now, how are we going to get our y values? Well, we're simply going to get our y values by plugging those x values into each of the functions. So I'm probably going to have to show you, so what happens when I plug this -2 in right there and for that x? Well, you're going to have 2 to the -2. And if you recall, the rules for negative exponents is you flip them over and they become a fraction. So this becomes 1 over 2 to the second, which is 1/4. So this number is 1/4. Similarly, if I do 2 to the -1, that's simply going to flip that over and make it 1 over 2 to the first. So that's 1/2. Now, when I plug in a 0 into that function, 2 to the 0 power, anything to the 0 power is 1. When I plug in a 1, 2 to the first is 2, and 2 to the second is 4. So that's how we got those y values. We plugged all of these x values directly in for the x right there. Okay. Now I'm going to do the same thing for these x values, but they're going to get plugged in right there. And I want you to see what happens. So now instead of taking 2 to a power, we're taking 4 to a power. And so what happens with the negative numbers is we end up getting 1 over 4 to the second. So if I plug in 4 to the, whoops, change the color here. 4 to the -2, that is 1 over 4 to the second, which is 1/16. So that's much smaller than whenever the other function had. When we do with -1, we're going to get 1/4. And then when we plug in 0, it's 1. Anything to the 0 power is 1. And then 4 to the first power is 4. 4 to the second is going to be 16. So what you see if you compare these y values, I'm going to highlight them. If you compare the y values, those, for the 4 to a power, they're much smaller. 1/16 and 1/4 is a lot smaller than 1/4 and 1/2. Now, but when you get into the positive x values, you can see that they get a lot bigger. So that goes all the way up to 16 as opposed to 4 in the other one. So now we're going to go ahead and sketch a graph of both of those. And I'm going to put them on the same coordinate plane just so you can kind of compare to what they look like. So there's my coordinate plane. I'm going to go out to 2. I have a -1 here, and -2, and +1, +2. And then I'm going to go up. Oh, how much do I want to go up? Maybe, I don't know that I'm going to go up 16. I'll probably just go up 4. Give you an idea. Okay, so we're going to go ahead and graph the red one. -2, 1/4. That's really pretty small. Maybe a little bit higher than that. We'll say about right there. And then we have -1, 1/2, which would be probably about there. Then 0, 1, 1, 2, and then 2, 4. So what you see is a nice graphed function. That right there is f of x equals 2 to the x. Now I'm going to graph 4 to the x. And so when we start back here, this number is going to be much smaller. It's only -2, 1/16. And then we have -1, 1/4, which is still much smaller. But then we get to 0, 1, and it ends up crossing the same exact point on the red graph. Then we go to 1, 4, which is up here. and then 216, which is going to be way up here. So that you can see this stays flatter for a little bit, and then it kind of goes through the same point and then shoots up a lot faster. That's what the graph of 4 to the x is going to look like. So there's a comparison between the two. So what I'm hoping for you to see from here is how this base number affects the graph. So if the base number is a little closer to 1, it's going to be much flatter at the beginning, and then it's going to shoot up. And if that base number is bigger than 1, it's going to be even flatter and shoot up faster. And there's a comparison of the two graphs. That's an actual graph with the tables written side by side, which is exactly what I just showed you. Now let's talk a little bit about what a exponential graph looks like. This is kind of a summary of its characteristics. First of all, the domain of this function is negative infinity to positive infinity. So that means this graph goes to the right forever and it goes to the left forever. There is no domain restrictions, or there are no domain restrictions on an exponential graph. The range is not negative infinity to infinity. The lowest that an exponential graph is going to go is the x-axis right here, but it actually will not touch the x-axis, which is why you see that there's a parentheses on the 0 and not a bracket. So that means up to, but not including 0 to infinity. The y-intercept of the basic exponential function for all of them is going to be 1. And that is because anytime you take anything to the 0 power, you will always get 1. It is an increasing function, and it's increasing if the a value, if this a value is bigger than 1. If it's not bigger than 1, it will not be an increasing function, which I will show you here in a second. And it has something called a horizontal asymptote. Now, we haven't really talked too much about asymptotes yet. We will in the next section after we're through this exponential growth and the student loan stuff. But what an asymptote is, it's kind of like an invisible border that a graph goes and it approaches, but it never crosses. And so there is an asymptote right there on the x-axis. The last thing is it is continuous. Now here's what an exponential decay function looks like. And there's a couple ways to get an exponential growth versus exponential decay. The first way to get exponential growth is the a has to be greater than 1 and or the power has to be a positive power. Now, if you change this to where the power is a negative, or the a number is between 0 and 1, that will give you a decay. And I'll give you more examples of that if it's a little bit still confusing. But as you can see with decay, it's just a reflected version of the original function. You can see the negative is directly on the x, so that is a reflection on the y-axis. So it takes this graph right here and it flips it over and just makes it look like that. So when that x is negative, we get a reflected version of that, and it's an exponential decay. And it is also, it does also have a domain from negative infinity to infinity. The range is still the same. It's 0 to infinity, but not including 0. And it also has a y-intercept of 0, 1. But this function is decreasing because as you trace it from left to right, it is going down. And there is a horizontal asymptote on the x-axis, and it is continuous. Okay, so it says, as a result, the graphs of the horizontal line test, and as a result, the graphs pass the horizontal line test, and therefore the functions are one-to-one. And because they're one-to-one, that means they have inverses, which we will talk about how to figure that out. Now, I'm going to go ahead and scratch this out. I'm going to pretend like these aren't here because I want to work you through each step and how this works. But what you see here is we have this I look at these as almost like puzzles, right? It's an equation. You can see that we have a missing value, and we need to figure out what x should be so this equation is the same. Now, the way these work is they ask you to use the one-to-one property to solve. And so what you need to do is rewrite the bases so they are the same. And so what you see here is we have this base, which is a 3, and this eventually is going to be a base of an exponent. It's a 9. We need to rewrite that 9 so it's the same as the 3. So what we do is we rewrite 9 as 3 to the second, and then that equals 3 to the x plus 1. Now what you can see is these bases are the same, and since this states they have to be equal, If the bases are the same, then the powers must be the same. And so then we're going to set those two powers equal to each other. We're going to set 2 equals x plus 1. And we can solve by simply subtracting 1 from both sides. And there's our solution, x equals 1. We're going to try another one of these. This one is a bit trickier. Again, I'm going to get rid of all this. I don't want you really to pay attention to this, although it is the right answer. This one's a little harder because of it's going to utilize some more exponent rules that you might have gotten a little rusty on. But we're same directions as the last one. We need to solve this. And so we can see we have this 1/2 here and we have this 8 here. We need to somehow get those two numbers rewritten so they are the same base. Now, I think the easier of the two is the 8. Hopefully that you know that 8, we can rewrite that as a base to a power. That is 2 to the third power. 2 times 2 times 2 gives me 8. So I'm going to rewrite the 8 as 2 to the third. But what we got to do with the 1/2, it's a little bit more convoluted. So what I want you to recognize is that this is 1 over 2 to the first power. Now, there is a rule that tells us that if I have a base, let's say it's a 3, to a negative power, we flip that over and make it 1 over 3 to the fourth. And you learned that. I'm actually teaching that power right now in my Algebra 1 classes, but it's been a while. So what that rule allows us to do is it allows us to take something with a negative power and put it down to the bottom, and then the power becomes positive. But it also allows us to do that in the opposite direction. If we have something on the bottom with a positive power, we can bring it up top, get rid of the fraction, and just make the power negative. So that's exactly what I'm going to do here. I'm going to take this 2 to the first, and I'm going to bring it up top here. And when I do that, it is going to make the 2 to the negative first power. All right. Now, all of that is still being taken to the x power. Now, the next exponent rule we're going to utilize is the power to a power. When we have a power to a power, you multiply. As an example, if I had, I don't know, x squared to the third, that would be equivalent to x to the sixth. So I'm going to go ahead and multiply those two numbers together, the x and the negative 1. And when I do that, I get 2 to the negative x equals 2 to the third. So now we finally have our bases rewritten. The 2's are the same, which means we can set negative x equal to 3. And when I divide by negative 1, I get x equals negative 3, just like that. And there's our answer. Okay, that's what I have for you today. Thanks for listening. And as always, if you have any questions, feel free to email me. Have a great day.